Hello everyone, this is Amika Mahajan. Welcome to my channel. This video is focused on some important questions from optics of class 12. Basically, most of the questions are from previous CBSE board papers. A convex refractive index 1.5 is kept in a liquid medium having same refractive index. What is the focal length of the lens in this medium? Converging lens means I am talking about convex lens. So refractive index of lens is 1.5 and medium also has refractive index 1.5. Focal length is given by n-1 into 1 by r1 minus 1 by r2 equal to 1 by f. Now, because this n is equal to refractive index of this lens divided by refractive index of this medium. N will be final medium lens on which rays are incident while traveling from this medium which has refractive index nm. So this will be the formula for n. But because refractive index, both refractive indices are 1.5, so this term will be 1. When I put this in this equation, then 1 minus 1 will be 0. So 1 by f is 0. When we get answer 0, if I take reciprocal, then f will be 1 by 0. Anything divided by 0 will be infinity. So f will be infinite value. Next question, 3 light rays, red, green and blue are incident on an isosceles angle prism ABC at face AB as shown. Explain with reason which ray of light will be transmitted to the face AC. The refractive index of the prism for red, green, blue light are given. Trace the path of ray after passing through face AB. We know that for internal reflection to take place, what happens? Angle of incidence should be greater than critical angle. Now, what happens? Here angle of incidence is 45 degree because it is right angle prism. Both angles are 45 degree. This angle is also 45. So what happens if I take this sine 45 and its reciprocal? First of all, take sine 45. It will be 1 by root 2. Now take reciprocal of this term. It will be root 2 less than 1 by sine c. And you know 1 by sine c is refractive index. So what happens? 1.414 is less than n. Or you can say refractive index. If is more than 1.414, only that color will be internally reflected. Now check here. There are 3 colors, 1.39, 1.44 and 1.47 are refractive indices of these colors for these colors in case of prism. Now, if n is greater than 1.414, check 1.414. These are these 2 colors. They have more refractive index as compared to this value. So these colors will be internally reflected, and 1.39 refractive index, which is for red color in case of prism, will not be internally reflected, rather it will be transmitted. So this will be the path of ray. For green, it will be internally reflected. For blue, it will be internally reflected, but for red, refraction will take place because here I has become less than C in case of red color. Next, how does fringe width of interference fringes change when the whole apparatus of Young's double slit experiment is kept in water of refractive index 4 by 3? We know that fringe width is given by lambda capital D upon small d. Capital D is distance of screen from the slit and small d is distance or separation between 2 slits. Now, if the whole apparatus is kept in water, then what happens? With change in medium, wavelength changes. So lambda dash will be lambda by n. N is refractive index. So new fringe width will be lambda dash into capital D upon small d. There is no change in these two values. Why? Because as it is, apparatus is immersed in water, now only medium is changing. So when I put lambda dash in this, what happens? What I get? 3/4 into lambda. Put this value here. It comes up to be 3/4 lambda d by d. What is lambda d by d? Already initial fringe width. So beta dash will be 3/4 times beta. Or you can say beta by 4/3 or beta by n. So fringe width will decrease. It will become 3b/4 now. Next, why is the interference pattern not detected when two current sources are far apart? That means these two slits, they are acting as two current sources. If these are far apart, this small d is very large, then what will happen? We know that fringe width is given by lambda capital D by small d. This small d is very large. As a result of which, if denominator becomes very large, then answer will be less. So B will be very small. So what happens? The fringe width will become very small, as a result of which fringes will not be resolved. That means separate fringes will not appear. That is why interference pattern is not detected when two current sources are far apart. Similarly, if we have two current sources infinitely close to each other, then again interference pattern is not detected. Why it is so? Again, fringe width is given by this relation. If small d becomes very less, infinitely small, if denominator is very small, then answer will be very large. That means fringe width will be too large. That single fringe may occupy the whole field of view. And we will not be able to observe interference fringe pattern. Only single fringe will be there, which will occupy the whole field of view. Other fringes will not be visible. That is why the interference pattern not detected when two current sources are infinitely close to each other. That means if two current sources are very close or very far apart, interference pattern will not be detected. If S is the size of source giving light of wavelength lambda, separation between slits is small d, and capital D is distance between source and screen, what is the criterion for the interference fringes to be seen? Criterion is size of source divided by distance between source and screen should be less than ratio of wavelength and separation between two slits. That means small S is size of the slit and capital D is the distance between slits and screen. This S by D should be less than ratio of wavelength and separation of the two slits. Thanks for watching this video. Like, share, subscribe my channel.